This topic is about being able to solve geometric problems involving vectors in 3 dimensions. So let's go through a few examples. So the points A, B, C have coordinates 2, 1, 5, 4, 4, 3 and 2, 7, 5 respectively. Show that triangle ABC is isosceles. So because they're coordinates, I can change them into vectors, because I can change them into position vectors. So from O to A, position vector is 2, 1, 5. From O to B, it's 4, 4, 3. And O to C is 2, 7, 5. So I need to show ABC is isosceles, so I need to work out the magnitude of A to B, and then B to C, and then A to C, and two of them must be the same for it to be isosceles. So first let's work out A to B is equal to A to O plus O to B, which is equal to minus 2 minus 1 minus 5 plus 4, 4, 3, which gives me 2, 3, minus 2. So the magnitude of A to B is equal to the magnitude of 2, 3 minus 2, which is square root of 2 squared plus 3 squared plus minus 2 squared, which is equal to 4 plus 9 plus 4 square rooted, which is square root of 17. Okay, I need to do the same thing with B to C now. So first I need to work out B to C. So B to C is equal to B to O plus O to C. So B to O is minus 4 minus 4 minus 3 plus 2, 7, 5, which gives me minus 2, 3, 2. So the magnitude of B to C is the magnitude of minus 2, 3, 2, which is equal to square root of minus 2 squared plus 3 squared plus 2 squared, which is equal to square root of 4 plus 9 plus 4, which is equal to square root of 17. So we just found that A to B and B to C. So if I were to draw it out again, labeled it wrong. This is A, this is B, this is C. And what I've just worked out is A to B is square root of 17 and B to C is square root of 17. So now all I need to prove that it's isosceles is show that A to C is not square root of 17. So I have to work out A to C now. So A to C is equal to A to O plus O to C, which is equal to minus 2 minus 1 minus 5 plus 2, A to O plus O to C. Okay, plus 2, 7, 5, which gives me 0, 6, 0. So the magnitude of A to C is equal to the magnitude of 0, 6, 0, which is equal to 0 squared plus 6 squared plus 0 squared, which is square root of 0 plus 36 plus 0, which is equal to square root 36, which is 6. So A to C is 6. So since A to B, the magnitude of A to B is equal to the magnitude of B to C, which is equal to root 17. Therefore, two sides of triangle ABC are of equal length. Therefore, ABC is isosceles. find the area of triangle ABC. So if I know, for example, this is, I've got triangle ABC. I know the whole thing is 6, so if I half it, I know this is 3 and this is 3. I know this is root 17. This is a right angle triangle, so if I just draw that part out, I've got 3 root 17. So if I want to work out this must be 17 take away 3 squared square rooted, which is equal to square root of 8, which is equal to 2 root 2. So the area of this triangle, this triangle is half times 3 times 2 root 2, which is equal to 3 root 2. Therefore, because it's double, so you can see here, you've got 2 of those, you have to double it. So area of triangle ABC will be equal to 2 times 3 root 2, which is equal to 6 root 2. Okay, C now. It says find a point D such that ABCD is a parallelogram. Okay, so we have so if I draw out the triangle again, we know A to B is the vector 2, 3, minus 2. So from A to B, we have the vector 2, 3, minus 2. Okay, and we know B to C is the vector minus 2, 3, 2. So B to C is minus 2. Let's redraw this because I feel like I've done a mistake. So a triangle looks something like this, okay? A here, B is here, and C is here. So we know A to B is equal to 2, 3, minus 2. B to C is equal to minus 2, 3, 2. And A to C is equal to 0, 6, 0. So 0, 6, 0. So now D is a point, so it's a parallelogram. So D can be either here, here, or there. So there's 3 different possibilities. We're going to go with this one. So if I want to find this one here, one possibility is because it's parallel to 0, 6, 0, I need to travel from B to 0, 6, 0 to get my answer for D. So this is D. This is a possible answer for D. So for part C, I need to do O to D because I want to work out the point D must be equal to O to B. So remember, everything starts off from the origin, which is somewhere here. O to B plus B to D. Now O to B is just 4, 4, 3. 4, 4, 3. And B to D is just the same as A to C, which is 0, 6, 0, because B to D is parallel to A to C, which means I end up getting 4, 10, 3. Therefore, D must be equal to, D must be the point 4, 10, 3, because this is obviously the position vector, which is relative to the origin. So it's 4, 10, 3. Okay, next question. The point A and B have position vectors 10i minus 23j plus 10k. So it's A is equal to 10 minus 23 and 10. And B is equal to P 14 and minus 22. Relative to a fixed origin O where P is a constant. So we've got O to A is equal to 10 minus 23, 10. And O to B is equal to P 14 minus 22. Given that OAB is isosceles, find three possible positions of point B. So before we do anything, let's work out what A to B will be. Then A to B will be equal to A to O plus O to B, which is equal to minus 10 positive 23 minus 10 plus P 14 and negative 22. So we end up with P minus 10, 37 and negative 32. Okay, so we have three situations. So case 1 is when if the magnitude of OA is equal to the magnitude of OB, then therefore this implies that we get O to A, the magnitude of that is 10 squared plus minus 23 squared plus 10 squared must be equal to square root of P squared plus 14 squared plus minus 22 squared. Which implies, let's get rid of the square root and simplify. So 10 squared plus 23 squared plus 10 squared gives us 729. And P squared remains there. 14 squared plus 22 squared gives us 680. Which implies P squared is equal to 49. Which implies P is equal to plus or minus 7. And let's do case 2 now. Case 2 would be if magnitude of OA is equal to the magnitude of AB. That implies OA is just again 10 squared plus minus 23 squared plus 10 squared is equal to A to B is going to be P minus 10 squared plus 37 squared plus minus 32 squared. If we get rid of the square root and we simplify, we get 729 on this side. If we expand the P minus 10 squared, we get P squared minus 20P plus 100. 37 squared plus negative 32 squared is plus 2393. If we take everything to the right hand side, I end up getting P squared minus 20P plus 1764 is equal to 0, which means P is equal to minus B, so it's 20 plus or minus, using the quadratic formula, this is times minus 20 squared minus 4 times 1 times 1764 all over 2 times 1. But here we get a discriminant, which implies the discriminant is equal to minus 6656, which is less than 0, therefore no solution for case 2. So case 2 has no solution. We need to go to case 3 now. So case 3 is if O to B is equal to A to B, which implies that O to B is square root of P squared plus 14 squared plus minus 22 squared is equal to, put the square in the wrong place, is equal to the square root of P minus 10 squared plus 37 squared plus minus 32 squared. So on the left hand side, if we get rid of the square root and we simplify, we get P squared plus 680 is equal to P squared minus 20P plus 100 when we expand the bracket, plus 37 squared plus 32 squared is plus 2393. Get rid of the P squareds. So if I move the 20P over to the on the left hand side, I get negative 20P, and to the left hand side I get positive 20P. 2393 plus 100, take away 680 gives me 1813. P must be equal to 1813 divided by 20. So that's my other solution. So I've got 3 different values for P. Therefore, B would be equal to either P is 7, so 7, 14 minus 22, or B is equal to negative 7, 14, negative 22, because P is negative 7, or B is equal to 1813 over 20, 14 and minus 22. So these are our solutions. Okay, the next question. The diagram shows cuboid with vertices O, A, B, C, D, E, F, and G. So cuboid. Vectors A, B, C are the position vectors of the vertices A, B, and C respectively. Prove that the diagonals OE and BG bisect each other. So OE is here and BG is there. So let's call this point of intersection X. So let X be the point of intersection of O to E and B to G. Okay. And then O to X. So we want to find 2 different routes from O to X, yeah? So the first way to get from O to X is from O to X, which must be equal to lambda times O to E, since X lies on O to E. So we have to work out what O to E will be. O to E is the same thing as O to A plus A to G plus G to E, which is equal to A plus C plus B, which is the same thing as A plus B plus C. So I can write OX, which is equal to lambda times OE, is just lambda times A plus B plus C, which if I expand gives me lambda A plus lambda B plus lambda C. But another way to get from O to X is also going from O to B, through O to B and then B to X, which is just O to B plus a scalar multiple, mu, let's say, because it's not the same scalar multiple as before, mu times B to G, as X lies on B to G. So now I need to work out what B to G is. Now B to G is the same thing as B to O plus O to A plus A to G, which is equal to minus B plus A plus C. If I rewrite it, it's A minus B plus C. So O to B is just, I can rewrite this as O to B is B plus mu times B to G is what I've worked out now, which is equal to A minus B plus C. If I collect the A's, B's and C's together, I get mu times A plus 1 minus mu times B plus mu times C. So if I equating A, B and C in equation 1 and 2, I get lambda is equal to mu for A, and for B I get lambda is equal to 1 minus mu, and for C I get lambda is equal to mu, which means the second equation becomes lambda is equal to 1 minus lambda, which means 2 lambda is equal to 1, which means lambda is equal to half. If lambda is equal to half, it means mu is equal to half. So therefore, O to X is equal to half times O to E. So X bisects O to E. And also we have B to X is equal to half of B to G. So X bisects B to G. Therefore, diagonals O to E and B to G bisect each other at the point of intersections, at the point of intersection, which is what we're trying to prove. Okay, so the whole skill here, what you need to do is find two different routes for getting to the middle, and then equate them. So here's another example. It's very similar. So a parallelepiped is a three-dimensional figure formed by 6 parallelograms. The diagram shows a parallelepiped with vertices OA, B, C, D, E, F, and G. A, B, C are vectors OA, OB, and OC respectively. Prove that OF and AG bisect each other. So O to F is here, and A to G is there. Oops, let's draw that properly. So let's call the point of intersection X. So it's very similar to the proof. Let X be the point of intersection of OF and AG. Then remember, two different ways from O to X. Then O to X is equal to lambda times O to F, as X lies on OF. So I need to work out O to F. O to F is equal to O to A plus A to D plus D to F, which is equal to A plus B plus C. So I can rewrite lambda times O to F as lambda times A plus B plus C, which is equal to lambda A plus lambda B plus lambda C. So this is my equation 1. Similarly, O to X is also equal to O to A plus A to X, which is equal to O to A plus a scalar multiple of A to G, as X lies on A to G. So I need to work out A to G first now. A to G is equal to A to O plus O to C plus C to G. A to O is minus A, O to C is plus C, and C to G is just B, which is equal to minus A plus B plus C. So O to A is just A, plus new lots of A to G is minus A plus B plus C. If I collect the A's together, I get 1 minus mu times A plus mu times B plus mu times C, which is my equation 2. So equating A, B, C in 1 and 2, I get, by equating the A's, I get lambda is equal to 1 minus mu. By equating the B's, I get lambda is equal to mu. And by equating the C's, I get lambda is equal to mu, which implies that lambda must be equal to 1 minus lambda, which means 2 lambda is equal to 1, which means lambda is equal to half, and mu is equal to half. Therefore, O to X must be equal to half times O to F. So X bisects O to F, and A to X is equal to half times a to g. So x bisects a to g. Therefore, diagonals OF and AG bisect each other at their point of intersection, which is x. Okay, last question I'm going to go through. The diagram shows a cuboid whose vertices are O, A, B, C, D, E, F, and G. A, B, C are position vectors of the vertices A, B, and C respectively. The point M lies in OM such that O to M to E is 3 to 1. So this is 3 to 1. And the straight line AP passes through M. Given that A to M to P is again 3 to 1, prove that P lies on the line E to F and find the ratio F to P to E. Okay, so the first thing I need to do is prove that P lies on E to F. So E to F is just equal to, E to F is equal to negative O to A, which is equal to minus A. So if P lies on E to F, it must be a scalar multiple of negative A. So let's work out how to work out F to P. So if I know this is negative A, I need to work out what F to P is. F to P is equal to F to B plus B to O plus O to A plus A to P, all the way like that. So it'll be F to B plus B to O plus O to A plus A to P. Now F to B is easy, it's just minus C because it's the opposite direction of O to C. B to O is just negative B because it's in the opposite direction of O to B. O to A is just A. The A to P we don't know what it is, but we do know if we know what A to M is, it's 4 out of 3 of A to M. Because if it's A to M is 3 parts and M to P is 1 part, then it's 4 over 3 of A to M. So what we need to do is work out A to M first, because that will help us. Now A to M is the same thing as A to O plus O to M. But O to M is just 3/4 of O to E. And so I've got A to M plus 3/4 of O to E, where O to E is just O to A plus A to G plus G to E. So O to A is A to G is plus C, and G to E is plus B. It's just A plus B plus C. Therefore, A to O is minus A plus 3/4 of O to E is what we just work out, A plus B plus C. So I end up getting minus A plus 3/4, which is minus 1/4 A plus 3/4 B plus 3/4 C. So if we go back to the original, I've got minus C minus B plus A plus 4/3 of what I've just worked out, which is minus 1/4 A plus 3/4 B plus 3/4 C. So I get positive A minus 1/3 A, which is equal to 2/3 of A. Got minus B plus B, which disappears, and minus C plus C, which disappears. So I'll get 2/3 of A as F to P, which is negative 2/3 times E to F, because E to F is just negative A. Therefore, P lies on E to F, as P is a scalar multiple of E to F. 3, as f to p is a scalar multiple of e to f. Next thing we need to do is find the ratio f to p to e. So I already know what f to p is, so f to p is equal to f to p. So I know f to p, keep writing this wrong, f to p is equal to 2/3 of a. So I need to work out p to e now. So p to e is equal to, if I do it in a different color, so p to e is equal to p to a plus a to g plus g to e. So p to a plus a to g plus g to e. Now p to a is 4/3 of m to a, which I worked out. I know a to m is here, so I can work out I've already worked out a to m, so I can work out m to a easy. Plus a to g, we can work out easily. A to g is just c, and g to e is just b. Now m to a is the opposite of a to m, so be 1/4 a, so I'm getting it from here. So 1/4 a, so opposite, so in the opposite direction, so I change the sign, minus 3/4 b, minus 3/4 c. Plus c plus b. So if I simplify this, I get a third a. I get minus b plus b and minus c plus c. So I just get a third a. So that means fp to p, f to p to e, the same thing as 2/2/3 a to a third a. So if I simplify that, it's the same thing as 2 to 1, which is what I wanted. I'm just going to rewrite that as minus 1/4 a plus 3/4 b plus 3/4 c.